Very pleasant morning, respected dignitaries and members of faculty. Warm welcome to a one-week faculty development program online on electric vehicles, technological advancements and trends from February 20 to February 25th, 2026. Organized by Vasreddy Venkatadri Institute of Technology from Tripoli Department in association with II Students Chapter. Welcome to the fifth session of FTP. Dr. Immanuel Anupalli was born in the year 1983 in Nellore, Andhra Pradesh, India. He obtained his BTech degree in Electrical and Electronics Engineering, MTech degree in Power System Operation and Control, and PhD degree in Electrical and Electronics Engineering from Sri Venkateshwara University, Tirupati, Andhra Pradesh, in the year 2006, 2011, and 2018, respectively. Presently, he is working as an associate professor in the Department of Electrical and Electronics Engineering and Dean Research and Development, Adisankara College of Engineering and Technology, Gudur, India. He published 14 papers in various reputed international journals, presented 12 papers in different national and international conferences, and also published two patents. At present, he is guiding three research scholars. He has 12 years of experience in teaching and of 7,75,725 under DST SEED, and also CEO of Atal Community Innovation Center, Adi Sankara Innovation and Incubation Center, worth of 5 crores sanctioned by AIM, Niti Ayog Government of India. He has delivered two guest lectures on fuzzy logic applications, an expert lecture on technical writing and research methodology in an AICTE sponsored 6 days online short term program, and also acted as session chair for the international conference ICG-PTPG 2019 at SV University, Tirupati. He is reviewer of three reputed international journals from publishers of Elsewhere and Taylor and Francis. He visited Germany to attend ARC 1.0 Lab FDP under the initiative of Indo-European Skilling Cluster for Mechatronics and Manufacturing by ECM, Aachen, Germany, and APSSDC, India in the year 2019. He also visited Hong Kong to attend international conference to present his research paper in the year 2014. He is a professional member of IEEE and IEEE Student Branch Counselor of IEEE Student Branch, ASCET. His interested areas are power systems, control systems, fuzzy logic, optimization techniques, and electric vehicles. It is my privilege to invite such a noble personality, our chief guest, Dr. A. Immanuel, sir, to start the session.
Good morning to one and all. Thank you for reading my profile. Nice reading. And first of all, I would like to thank my friend John Buxing for inviting me as a speaker, one of the speaker in this 1 week workshop on electric vehicles. I also thank the management of VVIT and principal sir and head of the department for giving me an opportunity to speak or share my views in this workshop. And I also thank the management of Adi Sankara Group of Institutions for providing me an opportunity to serve in different leading positions in the Adi Sankara Group of Institutions. Let me share my presentation, then I'll start my presentation. Is it visible?
Yes, sir.
Yes, sir.
So, okay. So my title or selected topic is emerging trends in batteries, motors and controllers. 1 minute. So I'll stop my video. Okay. So this is the outline of my presentation. Introduction, EV batteries, emerging batteries for electric vehicles, charging and swapping infrastructure, EV motors, EV controllers, and some test results. So before going to talk about the batteries, motors, and controllers, so I would like to give some brief introduction to electric vehicles and why we are going for electric vehicles, why the people are focusing, not only people, even the government and world is looking towards the electric vehicles. So the electric vehicle is a vehicle that operates on electric motor instead of an internal combustion engine that generates power by burning a mix of fuel and gases. Electric vehicle is seen as a possible replacement for the current generation automobile in near future to address environmental challenges. So as we all know, at present, the transportation vehicles running on fuel or gas, that is petrol, diesel and gas majorly. So which are leading to result high carbon emissions, which may lead to environmental pollution. So therefore, the world is looking to have an alternate vehicle which can reduce these carbon emissions or environmental pollution. So in this context, the electric vehicles is one of the alternative good solution for the fossil fuel based vehicles. So these electric vehicles are inspired by road going automobiles powered by electricity, propelled by one electric motor or more using batteries. Electric motors give instant torque and smooth acceleration. These plug-in electric vehicles are fast, fun, and efficient. Maintenance is cheaper, simpler compared to the fuel. So where the fuel, the running cost of the petrol, diesel, gas is very, very high compared to the electrical energy stored in the batteries. So coming to the environmental pollution. So if you take the top 10 cities across the world, among top 10 cities, there are 7 cities of India present in top 10 polluted cities across the country. As we know, we only knows about New Delhi. Apart from New Delhi, you take Ghaziabad and Begusarai, Noida, Faridabad, and Sahasra and Birgan. All these 7 cities of our cities, which are uh, placing top 10 cities across the world. So you can imagine how the Indian cities are polluted and how danger it is to the living creatures in India. So therefore, it is inevitable to take some alternative steps to find a solution to reduce this environmental pollution. So therefore, in this place, I definitely assure that these electric vehicles plays an important role to reduce this environmental pollution. Coming to the top 20 world most polluted countries. So India is owning fifth place, whereas the if you see the previous graph, this Kashgar is a city in China. Though it is a first place, the China is occupying almost 13th or 14th place across the top uh, polluted countries in the world. So therefore, we have to take necessary steps against this environmental pollution and also reducing the cost of the fuel. So if you take the carbon emission reduction from the different uh, automobiles, see advanced IC engine, it can reduce up to 15% compared to conventional IC engine. Coming to the natural gas and biofuels, it can reduce up to 10 to 30% of carbon reduction. So if you go to hybrid fuel, hybrid fuel and electric vehicles, it may reduce 30 to 40%. Fully electric vehicles can reduce up 50 to 100%, or hydrogen based electric vehicles may reduce 50 to 100%. So therefore here, if we consider these three, hybrid fuel plus electric based and fully electric based hydrogen based electric vehicles, maybe the alternate solution which may reduce the environmental pollution and reduce the harmful gases from the environment. So therefore, because of all these reasons, these electric vehicles are gaining importance in choosing automobiles. And if you consider the number of deaths due to pollution, so in India, almost 2.51 millions of people or deaths is happening in a year. If you consider it, almost 8 times higher than the Pakistan, which is very close to us, and almost 16 times more than USA. So you imagine the Pakistan is also a very small country which is nearby us, and even in Nepal, one of the country which is highly polluted, one of the city which is highly polluted nearby India. If we consider the number of deaths due to pollution, so almost 8 times to the Pakistan and 16 times to the USA. So therefore, one has to look into this area in order to safeguard the environment and people's life. Not it is the measurement of the only people. Apart from people, there are so many living creatures on the earth which are affecting by the pollution. So therefore, it is the responsibility of each and every one to take some necessary steps against this environmental pollution, and it is also our responsibility to encourage these electric vehicles. So why these electric vehicles are so much popular and as gaining importance? So these are highly reliable and flexible. So electric cars requires less maintenance, and new models hitting the market also offer more flexibility of car size and style. And growing infrastructure. So earlier, so there were no charging stations. Even now also, there is a lot more focus has to be done to create infrastructure, especially in our India. Maybe the other countries have certain extent they created infrastructure, especially charging stations. You can plug your car in right at home, and more areas have charging stations for where you are on the go. And affordability. So electric cars are less expensive to fuel and maintain. As I told you already, so compared to the fuel based, that is petrol, gas, diesel based vehicle to the electric vehicle, the running maintenance is very, very less. But the initial cost is a bit high. However, we have to, the researchers have been doing doing their contributions in reducing the cost of electric vehicles. As new models come out, cost to buy electric cars are plummeting. And public health, as we discussed it so far, the electric cars don't spew the tailpipe pollution that's linked to asthma, heart attacks, poor health, and premature deaths. So therefore, because of all these advantages and concerns, the popularity of the electric vehicles has been increasing day by day, month by month, year by year, and we are going to expect a lot of advancements in electric vehicles. So coming to the electric vehicles, and the major parts of electric vehicle is battery and EV motor and EV controller. So these three are the major parts of the electric vehicle, any electric vehicle, whether it is two-wheeler or four-wheeler. Okay, battery, motor, and controller. The synchronization between these three devices are very much important to run any electric vehicle. And I would like to cover a few aspects of these three in this session. First, EV batteries. So basically here there are basically two types of batteries are there, primary and secondary batteries. The primary batteries are non-rechargeable batteries, whereas the secondary batteries are rechargeable batteries. So among the rechargeable batteries, there are different types of rechargeable batteries are there. Among all rechargeable batteries, the lithium-ion batteries are so popular due to its advantages. So the lead acid battery, if you see the lead acid battery, it is heavy and low energy density and toxic material. So its weight is very high. Though they sold a lot to the society because of its low energy density, so it is not that much preferable to the electric vehicles. Later, coming to the nickel cadmium batteries, the high cycle count, it is low cost, but it is toxic heavy metal and low energy density. So see here, if you see the graph here, the energy density of this lead acid battery about some 30 to 45 or less than 45. Where, and even the volumetric density also less than 90. The similar way, if you consider lead acid batteries, the energy density is about 55, less than 55 or 60. The volumetric density also less than 200. Then nickel manganese batteries, improvement in capacity over nickel cadmium, but high self. This nickel manganese batteries are highly self discharged. So therefore, they are also preferable. But compared to them, the lithium ion batteries are having a lot of advantages. They are having high energy density, and low self discharge, and low cost, and external electronics required for battery management. So these lithium polymer batteries, so they are having high volumetric energy density as well as gravimetric energy density, nothing but energy density or specific energy. So an external control is very much essential to operate these lithium ion batteries in a proper way. Coming to the battery chemistry and comparison. So here, lead acid batteries, the high power, and it is used for car batteries, EVs, and UPS. But there are its own merits and demerits. So it is simple, low cost, and low specific energy or poor energy weight ratio. That means its specific energy or energy density is less, means watt hour per kg is less for this lead acid batteries. And slow charge, it takes up to 14 hours, and it is highly toxic material. And however, it has advantage, low self discharge and limited cycle life. So however, it's like that. Coming to the nickel cadmium, it is fast and simple charging, low specific energy. It is a disadvantage, and good cycle life and shelf life, and it has some memory effect, and good load performance over temperature, toxic, not environmentally friendly, and economical and high self discharge. It also has some toxic. So like this here, if you come to the lithium ion battery, it has very high energy density, but required some protection circuit because the energy density is very high. That is, watt hour per kg is very high, and watt hour per volume is also very high. So relatively low self discharge, subjected to aging, even if not used. That is low maintenance. Because of high energy density, there are some transport regulations when shipping in high volume. So therefore, these lithium ion batteries are highly popular because of its high energy density, volumetric energy density, and low cost and light weight also. So key factors for selection of EV batteries. So while selecting the battery for electric vehicle, what are the factors to be considered? The one is the range. So at up to what range, that is speed in terms of kilometers. Charging time. So you have to select a battery in such a way that it should charge, it should not be fast charge and it should not be very slow charge. So it should be charged at least within 3 to 4 hours uh, when when you have sufficient time. Sometimes it has to charge within short time, less than 45 minutes or less than 1 hour also. That is often, not all times. And the weight is also constrained because we are placing these batteries in electric vehicles. So always weight and size is always matters. That is weight and volume. And safety concerns, you all knows, though there are a lot of advantages of electric vehicles, still people are worrying about its safety concern, that is thermal runaway or fire accident. So therefore safety also one of the major concern while selecting the battery for electric vehicle. And connectivity and communication. So so you have an electric vehicle. So when your vehicle should have a proper connectivity and communication with the especially charging stations. So if you take fuel-based vehicles, IC vehicles, so its communication is very easy. So wherever you go, you can communicate with any petrol pump to take the fuel. But it is not the case for the batteries. We will discuss that later. And the cost. So cost also major factor because in the battery in electric vehicle, the cost of the battery occupies around 40 to 45% of the vehicle cost is due to battery cost. So at now, so therefore you have to consider the cost of the battery also while selecting for electric vehicle apart from range, weight, volume, and its charging time and safety concern. Now, why lithium ion is so popular? Lithium ion batteries are so popular. As I told you multiple times, so a high performance battery for high performance devices. So everyone expect the high performance devices for their vehicles. So what are its advantages? So gravimetric energy density are nothing but specific energy or energy density, high capacity, lightweight battery, volumetric density energy, so high capacity and very thin battery, and low self-discharge, stays charged when not in use. So these are all the advantages a battery or a consumer or a customer expects from his battery. So low self-discharge, okay, when it is not in use, it should not be discharged, and it should be as thin as possible, and its weight should be as small as possible, and it has to give long mileage. When it has high energy density or high volume energy density, it gives long mileage. So even if you think, if you consider the periodic table, this lithium occupies the third position, very light material. So therefore, its weight of the lithium is also very, very less. So coming to the lithium ion battery chemistry, so there are different lithium ion batteries are there. So lithium cobalt oxide and lithium iron phosphate, which is called popular known as LFP, and lithium ion manganese oxide LMO, lithium nickel cobalt aluminum oxide NCA, and lithium nickel manganese cobalt oxide NMC, and lithium titanate. So among these, the lithium cobalt and lithium phosphate, then LMO and NMC, NCA batteries, or each one has its own merits and demerits. However, see, if you take LCO, it is generating 3.6 volts nominal cell voltage. Again, LMO 3.7 and NCA 3.6 and NMC 3.6. So these are the Lithium cobalt oxide batteries are used in cell phones, cameras, laptops. LFP batteries are used in power tools, medical, electric vehicles. LMO, power tools, medical, electric vehicles. And NCA, grid storage and electric vehicles. NMC, power tools, medical, electric vehicles. And this LTO, lithium titanate, the grid storage and electric vehicles. And this is the spider chart of these five types of lithium ion batteries. So if you take, if you consider this lithium, nickel, manganese, cobalt batteries, so it has high specific energy and it is specific a bit. If you take four, this is 100%, it is 75% of specific power, and safety concern also bit low, and performance also above average, and lifespan is also good. Cost is also high here. So therefore, while selecting battery, so one should a battery should have high specific energy, high safety concern, high safety, high performance, high lifespan, and cost must be low. So one has to choose a battery in such a way that it should have high specific energy, more safe, and should offer high performance and long life but less cost. So this is somewhat better. Whereas here, coming to the LMO, all are moderate, and see lithium iron phosphate battery, the specific energy bit less, whereas it is highly safe, and its lifespan is very high, and cost is also moderate. So therefore, that's why see here lithium titanate battery, though it is its performance is very high and lifespan also good, cost also less. Okay, but its specific energy is very low compared to. That's why it is less used compared to these three. These three are widely used. However, there are a good number of applications for all lithium-ion batteries. It's all depends upon selection and customer choice. Then, emerging batteries for EV. So, nanobolt lithium tungsten batteries. So, this is advanced battery. In a battery anode materials, tungsten and carbon multi-layered nanotubes added that bond to the copper anode substrate and built up a web like a nanostructure that forms a huge surface for more ions to attach to during recharge and discharge cycles, helps tungsten battery faster, and it also stores more energy. This is one alternate. And zinc manganese oxide batteries. So its chemical conversion reaction in a zinc manganese oxide battery, if controlled, it can increase energy density in conventional batteries without increasing the cost. And it makes a possible cheap alternative to lithium ion and lead acid batteries, provided it should have proper control circuit. And the organosilicon electrolyte batteries. A problem with lithium ion batteries is the danger of the electrolyte catching fire or exploding, as I told you. In lithium ion batteries, University of Wisconsin, Madison developed organosilicon based liquid solvents. The resulting electrolyte can be engineered at the molecular level for industrial, military, and consumer lithium ion battery for EV markets. And lithium sulfur batteries. A lithium sulfur battery uses very light active materials, sulfur in the positive electrode and metallic lithium as a negative electrode. You know, the electrodes are changing, however, lithium is acting as electrolyte in lithium ion batteries. This is why its theoretical energy density is extraordinarily high, 4 times greater than of lithium ion. That makes it a good fit for the aviation and space industries. More energy density in small pace as required in electric vehicles. And solid state batteries rather than liquid. So in a modern lithium ion batteries, ions move from one electrode to another across the liquid electrolyte, as I told you now. In all solid-state batteries, the liquid electrolyte is replaced by solid compound, which nevertheless allows lithium ions to migrate within it. The advantage is improvement in safety at cell and battery levels. Solid electrolytes are non-flammable when heated, unlike their liquid counterparts. Solid-state battery electrode permits the use of innovative high-voltage, high-capacity materials, enabling denser, lighter batteries with better shelf life as a result of reduced self-discharge. And this zinc air batteries is an advancement in the batteries. Instead of electrolyte lithium, the air is using as the medium. IIT Madras researchers are developing mechanically rechargeable zinc air batteries. Zinc is widely available in India and would reduce the import of lithium ion batteries. You know, though lithium ion batteries are so popular, the India doesn't have lithium reserves. I think recently the government of India identified some lithium reserves in Jammu Kashmir. Around, they mentioned around 59 millions of tons. I don't know exactly, around 59 millions of tons, I think. But so far we are importing the lithium-ion batteries from abroad, especially from China and Japan. The zinc is cheaper as compared to the lithium-ion batteries, while lithium-ion batteries cost $200 to $250 per kilowatt hour, whereas zinc air batteries cost around 150 kilowatt hour, $150 per kilowatt hour. With the wider usage, the price expected to come below $100 per kilowatt hour. It's obvious. The zinc air batteries are also water based and have a longer shelf life. Zinc air batteries have good turnaround efficiency. So not only IIT Madras, and I think IOCL is also working on the zinc air batteries. I think I read one column in one of the newspaper. And the reasons for thermal runaway. This is what this is what one of the main drawback of the lithium-ion batteries and the concern of electric vehicles. So there are three main reasons for thermal runaway: the mechanical stress and operating stress and the thermal stress. So this leads to cell temperature increase and internal short circuits when operating stress comes, when the uh, charging of the battery less than the minimum state of charge or greater than maximum state of the charge, and the current is greater than the maximum current. So because of this mechanical, operating and thermal stress, so there is some internal short circuit leads to internal heating, cell temperature rise. So maybe the internal short circuit or internal heating and cell temperature rise leads to the thermal runaway of the battery, and it is an exothermal reaction. So therefore, one has to address this thermal runaway issue. Thermal runaway. So how best we can address this thermal runaway or catching fire? Okay, that is through a battery management system. Battery management system. So what is battery management system? BMS for battery safety and avoid thermal runaway. So a battery management system monitors various parameters of the battery and prevent unsafe operation of the battery and communicate with the vehicle units like charger, controller, and etc. to safely operate lithium-ion battery-powered electric vehicles. So the battery management system uh, monitors, senses the different levels, voltages, currents, battery voltages, controller voltages, inverter voltages, and motor voltages, and it sends information or communicates information to all the devices to on, off, and reduce their time of operation. And what are the different functions of BMS, battery management system? So to protect the safety of the battery, operated devices, operator, detection of unsafe operating conditions and response accordingly, to protect cells of battery from damage in abuse or failure cases, to prolong life of the battery, to maintain battery in a state in which it can fulfill its functional design requirements. to help in the best use of the battery pack, example, power limits, control charges, etc. So these are all various functions of the battery management system. And it considers, if it considers, you see, a cell monitoring. So it monitors the cell voltage, cell current, a temperature, and here the state of heat estimation. So based on the state of heat, it can measure the end of life of the battery. And cell balancing, the voltage mismatch, multi-cell charge or discharge. Sometimes due to aging, after multiple operations of the battery, the voltage of the each cell sometimes gets reduced. So the BMS system monitors and manage the cell voltage by connecting the additional cell or to disconnect the cells. And the thermal management. So the temperature management, it measures the temperature of pack and its cooling system and also heat dissipation. The charge control, the rate of charge control and charging strategy, and state of charge estimation while charging and discharging, and its models and estimates the state of charge and state of discharge, and alerts the battery and alerts the other auxiliary parts of the. Sometimes uh, when the battery the close to depth of discharge, suppose if the depth of discharge is 80% of the battery, if the state of discharge reaches to close to 80 to 85%, you are running your vehicle, you have to reach a certain extent. So therefore it alerts the some of the auxiliary systems which are not much important to turn off them. It give alerts through BMS. And battery safety and protection is overcharge, over discharge, and short circuits. It senses the conditions of the battery and it alerts the battery and other protecting system to safeguard the batteries. So these are all the key functions of the battery management system. And this is the BMS system block diagram. So it has the master controller and local monitoring units. So each master controller controls or monitors around 8 local monitoring units, and each local monitoring unit controls the 8 cells of the battery pack. So, and the master controller collects all this information from the battery pack and sends information to the control area network. So this control area network take some decisions based on the conditions of the battery pack and cell and other temperature, other aspects, and it cut off or and continues the in parts or devices of the battery pack. So like that, this control area network controls this operation of master controller and local monitoring units in battery management system. Core competencies required for the development of BMS. So what are the different uh, skills or knowledge needed to develop battery management system? Analog and digital circuit design, microcontroller programming, PCB design, probability and statistics, and one could have awareness and control system, thermal analysis and simulation, battery chemistry, and communication protocols, because you have to send and receive information from the different parts of the battery. And this is the battery management system PCB. So this is master control unit, and these are the local monitoring units. So this is just a figure I gave you for information. And here these are the sensors, and this is lithium iron phosphate battery of 48-volt pack, and its BMS. And this is one live test results. So when we tested, we developed two wheelers with we have one. We are working with one electric vehicle manufacturing company, Bharat Alternate Fuels Private Limited, Bombay. and they design and developed two-wheelers. And we tested this 48-volt lithium-ion LF battery. So this is the test results. So if you observe the test results, this is the rate of state of charge. That is, while the vehicle is moving, the battery discharges from 100% to 0% or depth of discharge. And this red line indicates the discharge current, and this green line indicates the battery temperature. So initially the battery temperature started around 30 to 33, and it reaches to around 40, around 39, 38 degrees. And from there onwards, the battery temperature is constant. That is, it should be maintained at constant temperature. Otherwise, if the temperature of the battery rises, it may lead to reduce the lifespan of the battery. Sometimes it may catches some fire. And see here the speed. So here the speed of our designed vehicle maintained about 45 kilometer per hour. So that means if you maintain your speed constant, then you can get long mileage, more mileage. Otherwise, the mileage gets reduced if you increase the speed of the electric vehicle. So it is also one of the limitation. And coming to the half peak, sometimes there are some peaks. So while driving, testing the vehicle, sometimes on highway, whenever overtake is needed, so that times it draws some high current from the battery, leads to the peaks in the battery current. So this is all about batteries. So this is the batteries and battery management system. So now, so the electrical systems, electric vehicles have batteries, okay, and battery management system. Then, where to charge the batteries? Where to charge the batteries? So now we'll see a few aspects about charging and swapping infrastructure, especially by considering our Indian context. Coming to the charging and swapping infrastructure. So does charging swapping need standardization? So what to be standardized? Whether standardization is needed or not. So what standardization is a must? So here I will tell you once again about the fuel-based IC vehicles. So if you are running a car or a petrol-based car or a petrol-based two-wheeler, so on your way, wherever you go, you can take the petrol, irrespective of the petrol bunk, whether it is Indian Oil or HPCL or IUCL, okay, or really a private bunk. You can take the petrol from any petrol bunk because it is highly standardized. So there is no difference in quality and measurement of HPCL petrol, IOCL petrol, and Indian Oil petrol. So like that, here for connecting the charger, so it should be standardized. The plugs and sockets should be standardized for electric vehicles, but not yet done. Not yet done because the voltages and size of the batteries, rating of the batteries of different companies is different. So that's why the people has to work on standardizing these uh, uh, plugs and sockets. Voltage, current, and maximum power. So voltage rating of the charging point, current, maximum power, and communication to vehicle. So this is very much important. So what is communication to the vehicle? So this vehicle, so you know, if you go to petrol pump, so the petrol gun, pump gun, communicates to your vehicle. So it pumps the petrol or diesel to your vehicle from pump to your vehicle. So it is communicating to your vehicle. So like that, so in electric vehicles, this the charging plug must communicate to your vehicle. So what voltage I should give, what current I should give, what maximum power I should give, up to what extent I have to supply the energy, and where I have to stop. So this kind of communication should be happen between the charging station as well as your vehicle, as you are not carrying your onboard charger. And communication with energy supplier. Okay, so here you should have communication with supplier. So at what cost he has to supply energy to you, and charging operator or utility manager. Metering, how does one bill customer? So suppose you are charging your vehicle at some charging station. So how much you need to pay for charging your battery? So this has to be standardized. And protection, protecting your battery. And desirable standardization for swapping. So earlier we talked about charging. So when we are swapping the battery, that means you have to leave, if you want to leave your battery, and if you swap, you exchange your discharged battery with charged battery. So what are the standardization, what standardization is needed? The maximum weight, size of the battery, because if you have, suppose your vehicle has 2 kilo battery or 5 kilo battery, you cannot take 10 kilo battery for your vehicle, because it may be additional load to your battery. So the maximum weight and size also constrained, especially for two wheeler and four wheeler also. Okay, because so therefore the size and weight should be standardized for each category, like two wheeler or three wheeler and four wheelers also. So here a new business known as energy operator may carry out charging as well as swapping of batteries. I will discuss about the energy operator role in the next slide. And the logistics, stocks and finances, performance, chemistry, etc. need not be standardized. So inside the battery, okay, the electric vehicle doesn't bother about the inside chemistry. Okay, whatever it has, but give, it has to communicate with your vehicle, and it has to give long or better performance. And chargers at public place. So where to place these chargers? And at some point of time, the government of India suddenly announced that almost all the petrol bunks has to uh, install or provide the EV chargers. Is it possible to provide the charging stations, or is it possible to convert petrol bunks into charging stations? Certainly not, because the petrol pumps are designed for filling the petrol. That means if you take any petrol bunk, any vehicle which wants to fill the petrol, it comes and wait for maximum of 5 minutes. Very rare cases it's more than 5 minutes. After 5 minutes, it has to quit from the bunk. Otherwise, there is a huge traffic may occur at the petrol bunk, because no enough space at petrol bunk. It is designed for the vehicle entering and stays for 3 to 5 minutes, and it has to leave. So sometimes it may be possible when you have fast charges, less than 5 minutes. Is it safe for uh, electric vehicle? If you charge the battery less than 5 minutes, it's not safe. So therefore, the existing petrol bunks are not suitable for converting the petrol bunks into electric stations. So if they have large enough space, then it is okay. So therefore, so where we have to place these chargers at public places. So swapping at petrol pumps in 3 to 5 minutes is okay. Office and street parking, shopping, food complexes, okay, yes. So if you go to any shopping mall, at least you may stay half an hour, or at least sometimes 1 hour, sometimes 2 hours also. Some food complexes, sometimes half an hour, 1 hour. So at least a considerable amount of time. So therefore, you cannot block space for charging, but charge while being parked. So it is also one of the constraints. So one should not park the vehicles for charging at public places, which may lead to the parking issue. So that's why whenever you are parking your vehicle, you have to charge. So what kind of public chargers? Slow public chargers can be same as used in multi-story buildings. And fast chargers. Suppose if you have fast chargers, how fast, what kind of vehicles and batteries you have to consider, you have to think, and uh, have fast chargers. And what is the best charging strategy for extended battery life? Extended battery life. The best charge, slow at homes in nights, that is 2 to 3 hours slow charging at offices or parking lots will use onboard charger. So why we charge the batteries at nights? Why not daytimes? So the batteries should not be charged at low temperature as well as at high temperature. So if you are charging your battery at very, very low temperature, it takes more energy to charge from low temperature to the normal. At the same time, if you charge your battery at very high temperatures, its temperature juice rises more than the thermal coefficient. So therefore, it may lead to some temperature issues, or it can reduce the battery life. So that's why you have to charge your battery at medium temperature, maybe in between some 20 to 30 degrees centigrade. Especially for India, the temperature, majority of the southern places, the temperature is more than 45 to 50 degrees. So in daytime, so that is not safe for charging the battery. That is only occasional fast charging. That sometimes you are going for long distances, trips and vacations, and charging during restaurant visits. It may be some you can charge your vehicles for fast charging, but it is not advisable continuously. Buses and taxis may need regular fast charging because they can't wait for more time. So that's why it needs fast charging, especially for public transportation. Buses are used for public transportation, so therefore we cannot wait public for charging. And the battery swapping, that's what the energy operator. So what are the functions of energy operator? The energy operator sets up battery swapping infrastructure at convenient locations, maybe after every uh, 20 kilometers or 30 kilometers or 40 kilometers, because for two-wheelers the battery life may be at least 50 kilometers. So that's why it depends upon. And enroll customers who would lease EOS swappable batteries for their vehicle, because the batteries here, the swapping the batteries means a customer is going to the energy operator, and he has to hand over his dischargeable battery, and he collects the charged battery from the energy operator. So therefore, the battery energy operator has to invest a lot of money on the batteries, bulk as bulk charges. So that's why he has to enroll some specific number of, at least some specific market. He should have some confidence to run the business. So that's why he has to enroll some customers who would lease energy operators swappable batteries for their vehicles. EVO purchases and owns batteries, obviously, has bulk charges for charging discharged batteries. Customers pay for energy used in the batteries. And customers not only pay for energy use, he also needs to pay the cost of depreciation, interest on purchasing the batteries, infra, electricity cost, and operation cost. Because the energy operator is investing a lot of money on establishing the infrastructure as well as the batteries, swapping batteries. So therefore, if customer pays only for energy usage, okay, he can't get it revenue or his investment. So therefore, the charges may also include the cost of interest on purchasing the batteries and infra development, electricity cost. And not only for this, if the battery keep on using, the life of the battery is getting reduced. So therefore, some amount has to be paid on depreciation. So therefore, these are the different costs involved, especially while swapping the batteries. And another problem with swappable batteries, the swappable batteries cannot be charged anywhere except by EO at its bulk charges. What happens? Suppose if some customers take the batteries or swap their discharger batteries from energy operator, and they charges the batteries on their own charger multiple times without going to the energy operator. So the life of the battery gets reduced. And sometimes some people may run away by swapping their old battery with a new battery. Okay, and he can continue charging his battery at his doorstep. So therefore, these are the problems when the battery swapping stations establishes. So therefore, there should be a system called locked smart batteries. The battery should be smart locked, and they should not be charged apart from the EVO charging station. And and they should not discharge the energy to the unspecified vehicles. So they have to discharge the energy to the vehicle which is swapped for. So these for to safeguard from these two reasons. So the batteries has to be locked as a locked smart batteries. And as I told you, the cost of the battery occupies 40 to 45% of the cost of the uh, electric vehicle. So how best we can reduce the cost of the electric vehicles by managing the battery operating strategies. One is the range extenders. To use electric vehicles with two small battery slots. One would have fixed low cost limited range battery purchased along with the vehicle. The limited range battery, example, suppose 100 kilometers range for e-car and 50 kilometers for e-scooter. And use only night time for slow charging, so that gives maximum battery life. And there is second slot. The second would be an empty slot to add a range extension battery when needed. Swap in the second battery, doubling the range at petrol pump or energy operator, enabling another 100 kilometers range for e-car or 50 kilometers for two-wheeler. So swap the battery again for still longer range if you want more and more. So no public charger needed to wait for charging. Okay, you need not wait for any charging station. Okay, because there are swapping stations. You can go and discharge your battery. You can take the charged battery and you can continue your journey. And coming to the business viability for public transport, to make public vehicles affordable, how? Like this, split battery into smaller sizes, 1/3 and swap. No waiting time to charge the battery. So if you have 3 batteries of small size, so you can reduce the uh, initial cost of your vehicle. So smaller battery size makes EV highly affordable comparable to petrol vehicles. Okay, and no further economic challenges or technical challenges because you are not investing huge on uh, as initial cost. But engineering challenges for battery swapping need to be overcome. That's what I told you. So therefore, we have to work on that for having high perform swappable batteries. The battery life severely affected by fast charging at 45 degrees centigrade. So swapped battery chargeable in conditioned environment in 2 hours to maximize its life. Also possible to cool while charging. And battery cost reduction strategy. So increase energy efficiency of EV. Uh, so if you increase the energy efficiency of electric vehicle, it will itself reduces the 35 to 40% of cost of the battery. So it was done in the last 3 to 4 years. For e-autos, from 70 to 80 watt per kilometer to 45 to 50 watt per kilometer. Earlier, they used to take 70 to 80 watt per kilometer. That is motors and other auxiliary parts. Take 70 to 80 watt per kilometer. Now they are taking 45 to 50 watt per kilometer by increasing the efficiency of the motor and efficiency of the other auxiliary parts. E-buses from 1600 watt per kilometer to 900 watt per kilometer. See how drastically reduced. Then reduce battery size. Small battery will reduce the cost, but that will limit its vehicle range. So there will be always range anxiety when you reduce the battery size. So never an issue in ICE vehicles as a petrol tank costs are low. So this is the major difference because compared to battery cost, the tank cost is very poor. Everyone knows about it. Further, charging in vehicle battery takes long time, much larger than of filling petrol in ICE vehicle. So if you want to petrol the vehicle, uh, petrol, so you takes less than 1 minute or 2 minutes. But whereas for charging, at least 45 minutes is a fast charging also. So this is all about the batteries. Now I'll go to motors. So before going to talk about the EV motors in detail, first we should know the difference between the industrial motors and EV motors. So coming to the different attributes, the first attribute, the operating environment, typically at ambient temperature between 25 degrees to 40 degrees centigrade. So all industry motors may operate between 25 to degree because they are open to the environment. Whereas in EV motors, they are inside the vehicle, under the vehicle hood, near to engine, especially when it is hybrid vehicle. The ambience from 50 degrees to 100 degrees centigrade when it comes to the engine temperature as well as battery temperature and other parts temperature like motor temperature. So therefore, the temperature is a major concern here, the EV motors compared to industrial motors. And the duty cycle. The industrial motors are always, most of the times, they operate in continuous duty cycle and often intermittent in nature. Whereas the EV motors, they are highly intermittent in nature. And voltage classes, they typically from 110 volts to 11 kV. Whereas EV motors, it is 12 volts to 800 volts DC battery power. And efficiency classes, so this is some standards. So these industrial motors are highly standardized, their frame size, yoke size, and stator size, rotor size, and all. Whereas it is not standardized in the EV motors. And we are expecting the efficiency of the motor, EV motor, should be more than 90% for wide range. So if efficiency is more, it gives more mileage, Whereas operating frequencies, mostly it operates, the industrial motors operates about 50 to 60 hertz, well. Whereas EV motors operates up to 1 kilohertz to have more speed. And form factor and power density. So as I told you here, industrial motors are highly standardized. So the sizing of each and every part of the industrial motors are highly standardized. Whereas EV motors, there is no standard frame sizes. Okay, kilowatt per kg is different from different motors, different company motors. That depends upon the vehicle requirements. So it must be standardized. And cooling, for industrial motors, majority fan cooled, whereas for EV motors, sometimes natural cooling or air cooled or liquid cooling also. So cost per kilowatt, it is less as it is highly standardized and bulk manufacturing. So therefore, cost of the industrial motors is less compared to the EV motors because there is no mass production, okay, and not standardization. And these are the some standards, standard designs. So these are highly standardized, whereas these are not fully standardized, and standards are developed. I think there is a problem. I'll share my slide once again. No, what happened? Is it visible? Someone guide. Hello?
Yes.
Hello?
Okay, sir, audible.
So, what is visible on the screen? Difference between industrial motors and XCV motors. Is it right?
Yes.
Okay, okay. Then we'll go to So difference between the industrial motors and electric vehicle motors. So these industrial motors always operates at single operating point, whereas the EV motors operates at multiple operating points like this. So because of slip, it operates at single operating point, whereas EV motors operates at multiple operating points. And these are the applications of different electric vehicles. Here it is Hero cycle, 0.7 kilowatt hour. Ather is one of the leading electric vehicle, and Vvit Arrow, and this is. So here there is a differences e-mobility performance class overview for passenger vehicles: mild hybrid, full hybrid, and uh, EV, only EV battery. It is engine. Mild hybrid means it here the importance of electrical motor is very less. It just assists the engine. Whereas full hybrid, fully hybrid or plug-in electric vehicles, they share 50-50% around, depends. And this EV batteries, it is fully on battery based. So these are the ratings of maximum power rating, maximum speed, and DC voltage, generator side and motor side, and maximum current DC and AC. And application segments to EV motors like four-wheeler and buses. So 7.5 ton, 7.5 ton to 12 ton in mild hybrid and plug-in hybrid and pure EV based. So this is some self-explanatory. And see here, this is like a this is mild hybrid. So where motor contribution is very less compared to the engine. Whereas in hybrid electric vehicle, so when engine contributes maximum, the motor contribution is less. When motor contribution is maximum, the engine contribution is less. And the series fully hybrid electric vehicles, uh, both engine and motor contributes the equal portions. Whereas fully electric vehicles, the complete motor drives the electric vehicle. So while choosing, uh, they develop the highest level of torque for given current in the smallest package possible. So therefore here they should have high volumetric power density, high efficiency, high overload capability, high speed operation, and wide constant power speed ratio, high reliability and robustness, low torque ripple must be low, and minimum maintenance, less manufacturing costs, less acoustic noise, and easy of control and integrability. So this hybrid electric vehicle configuration, as I told you, parallel hybrid. I will show the figures. In parallel hybrid, both prime movers operates in the same drive shaft. Thus, they can power individually or simultaneously. Whereas in series hybrid, the electric motor drives the vehicle electrically provided by the battery or by the engine driven generator. Series parallel or combination hybrid has both mechanical link and electric link. I will show you the figures so that you can understand better. So this is the parallel vehicle configuration. So if you see the parallel hybrid EV, both engine driven drivetrain as well as motor driven drivetrain uh, connected to the wheel. Parallelly, they drive the vehicle. Whereas in series vehicle configuration, the generator is coupled to the engine, so it gives supply to the inverter. From the inverter, the motor gets the power, only motor drives the vehicle or wheel. This is about series and it is parallel. And it is the hybrid, which consists of both series and parallel. So the engine straight away, engine and motor straight away drives the vehicle, and also this engine coupled generator generates the power and supplies to the inverter, so that this system used in Prius and Estima hybrid. Okay, it has two motors, and depending upon the driving conditions, uses only electric motor or the driving power from both electric motors and the engine to achieve the highest efficiency level. Okay. And the classification of electric motors. So the motors are classified based on coil or winding to produce variable magnetic field, maybe concentric coil, distributed winding, or lap winding, wave winding. And permanent magnets to produce constant magnetic flux, and soft magnetic core to provide an easy path for flux in order to facilitate flux linkages or magnetic coupling between inputs and outputs. So here these are mainly classified based on these three factors: gap orientation and excitation type and power source. Here gap orientation is mainly based on these are the three types: radial flux type, axial flux type, and transverse flux. I will show you the figures so that you can understand better. Whereas excitation, induction type, reluctance one, and permanent magnet, hybrid. Hybrid means both. And this is alternating current and direct current. So for radial flux machine, perfect for low D by L configuration, where the torque is proportional to D square by L. So therefore it is perfectly low D by L and perfectly high D by L configuration. If D by L is high, the D square by L is still high. So therefore it can produce high amount of torque. So the radial flux machines are widely used, and these axial flux machines are upcoming now. And coming to the efficiency point of view, the axial flux machines gives about 96% of efficiency compared to radial flux machines. Where radial flux machines gives always efficiency less than 90%, whereas this axial flux machines gives 90% of efficiency, as it has two stators, single rotor, or single stator with two rotors. I will show you the figures so that you can understand better. So this is radial flux machine. So this radial flux machine consists of single stator and single rotor, and the flux is radially outwards, and the flux is axially distributed between rotor and stator. And this is the arrangement of the rotor and stator in radial flux machines and axial flux machines. So the axial flux machines, so here it has two stators and single rotor, sometimes two rotors and single stator. Because of that, the flux distribution is more. Due to that, the torque production is more, and it is compact machine compared to radial flux machine. Its size is very less. In less size, it can produce more amount of torque, high performance, so that it is very useful to the electric vehicles. So like this. So axial flux motor offers better power and torque than conventional motors. This is because they make better use of the available space, as I told you already, have larger cooling area and have larger active diameter. Okay, as they are not widely used due to lack of manufacturing and design experience in the industry. So that's they are just developing, and they will become popular in near future. And this is a motor topology of different different motors. This is induction motor, permanent magnet motor, switched reluctance motor, and synchronous reluctance motor. So here for induction motors, the power factor is less than 1. We know already, well aware of that. But efficiency is somewhat better compared to permanent magnet. Here, the not exactly equal to 1. It's close to 1, and its efficiency is very high. And synchronous reluctance motors efficiency is also high, whereas switched reluctance motors, the efficiency also better compared to induction motors, not much. And efficiency versus costing. So always the efficiency motor is proportional to the mileage of the electric vehicle. So therefore, performance evolution of EV motors, efficiency, energy per kilometer. The factor significantly affecting the efficiency is vehicle performance, depends upon speed, torque, and acceleration. Packaging, weight, and volume, that is energy density, volumetric density, and thermal management, the powertrain, the temperature, battery plus motor and controller, range and energy consumption. So these are all the factors which affects the cost of the motor or electric vehicle. Coming to the design challenges. So how efficiently did you design the powertrain to convert electrical, that is battery, fuel cell, or hydrogen to mechanical energy, or fuel to wheel efficiency? You see the efficiency of the different vehicles. ICE, that is gas-based ICE vehicle. ICE means internal combustion engine vehicle. The 14% as baseline. Hybrid electric vehicle, that is the other fuel is gas, 31%. The diesel-based hybrid electric vehicle, 37%, and fuel cell vehicle, 45%, and SFCV, 48%, and battery electric vehicles, 68%. 68%. So, for the best performance in electromagnetic design, minimize copper and lamination losses. In thermal design, use effective cooling methods. In mechanical design and manufacturing, use cost-effective, reliable methods and design for manufacturing and assembly. So you have to reduce the mechanical design cost, thermal cost, that is use of effective cooling. As I told you, 3 types of coolings are there. That is air cooling, water cooling, natural cooling. And here there is the maximizing total system efficiency is the biggest challenge in hybrid electric vehicles system design. And there is one fact here. A 0.5% improvement in motor efficiency is something that automakers will pay a premium for, because it is directly translates into getting more range without increasing the size of the battery pack. So you can get more mileage if you improve the performance of the battery, efficiency of the battery. And these are the different parameters to be considered while designing the motor. Electrical, there is number of phases, type of winding, current density, and number of turns. Magnetic poles, dielectric, that insulation, that is insulation between slot and strand, coil to coil, phase to phase, and phase to body, coil routing, and electrical breakdown. For lamination, to reduce the pore losses, and the thickness of the lamination should be considered, and magnets, energy to produce the magnetic field, which high flux density, shaft and frame, thermal, coolant, air, water, oil, so which should be considered, and mechanics, critical speed, acoustics, and the moment of inertia, forces during different operating points. And coming to the design, so first you have to take the specifications. What is the rating of the machine, kilowatt rating, and the RPM of the motor, and voltage of the motor, okay, and weight. So by taking all this, you have to select a machine topology, that is radial flux or axial flux, or induction motors, permanent magnet motor, or switched reluctance motor. So by taking this, you have to initial size the motor, okay, by rule of thumb calculations using some softwares and FE tools, okay, the speed, motor sol, motor CAD, and JMAC Cosmol. And after that, the electromagnetic, thermal, and mechanical design, that is loadings under threshold and saturation limits, performance estimation, duty cycle simulation, and design optimization. After that, study sensitivity to manufacturing. So noise and vibrations, material availability plus tolerance on manufacturing process, sensitivity analysis on performance with regard to manufacturing. Then compare designs and topologies. So you have to compare your design performance with the existing topologies. Then if build the prototype. After building prototype, test and compare. After comparing, if there is any modifications needed, you go to select the machine topology. Otherwise, confirm the design. And this is the thermal management. So the thermal management is very important. See here, this is the temperature rise, the winding temperature rise, and this is the average expected life in hours. When it is, there are different types of insulations are there, class A, class B, class H, and class F insulations. So depending upon the type of the insulation, the temperature withstand capability of the winding may vary. The class C has highest temperature withstand capability, class C type of insulation, about 180 degrees centigrade, and followed by class H less than 180 degrees. Like that, there are different types of insulations. So see here, if temperature is increasing, the average expected life in hours is being reducing. So at 60 degrees centigrade, say some class A has around some more than 1 lakh hours, more than 1 lakh hours. So when temperature reaches to 180 degrees or some 160 degrees, the average lifespan becomes very, very poor, about some hundreds, from lakhs to hundreds. So that's why the temperature rise plays vital role in the life of the motor. There is a basic rule of thumb. The lifetime becomes half for each 10 degrees rise over the rated temperature, multiplied by 2 for each 10 degrees centigrade below. So that's why the temperature levels are also important to avoid demagnetization of the permanent magnets and efficiency reduction. So investing in the cooling system optimization at the design stage of the machine can give significant long-term cost savings. So therefore, instead of losing the life of the motor, you better to have some cooling design to extend the life of the motor. So these are the different heat sources. The electromagnetic losses, Joule losses, nothing but copper losses, winding rotors, winding, as well as stator winding, as well as rotor winding losses, core losses, and magnets, that is permanent magnets, eddy current losses, and some mechanical losses like frictional and windage loss. These are the different sources to produce the heat, and we have to address this heat. Okay, and you know well aware of that how the iron losses and copper losses depends, and the magnet losses. Okay, and here mechanical losses, it is very difficult to model the mechanical losses. So therefore, the accurate modeling is very much essential in identifying the heat temperature rise, and in order to design the better cooling system. So design of cooling system. So as I told you, there are three types of cooling: the natural cooling, forced cooling, and liquid cooling. The natural cooling is used up to 1.5 to 5 ampere per millimeter square. The cooling efficiency is low, and complex, coming to its complexity, it is very simple. Whereas forced convection, its current density varies from 5 to 10 ampere per millimeter square. Its efficiency is medium and complexity also medium. Whereas liquid cooling, okay, you can go to 10 to 30 ampere per millimeter square, and its efficiency is very high, but it's complex. It is complex. Okay, so these two comes under active cooling. It is comes under passive cooling. The types of cooling require active and passive. Passive means natural cooling. Active means a method, a system to be used to cool the machine. So winding should respect the operating temperatures of their insulation classes. So as I told you, the insulation classes may vary from different. The magnet temperature should be far from their demagnetization threshold. So see here, so it is a fan, it drives cold air onto the machine or into the ventilating ducts, and it cools the motor winding. And here there are some channels. So see, this is a shaft. Even in the shaft, there is a channel to flow, and the outer layer has some channel to carry the liquid so that it absorbs the heat from the machine. And this is the physical diagram. Here there is a hole. Here it enters the water, and it comes through frame and leaves here. So therefore, it absorbs heat from the motor winding. So a good cooling doesn't mean the lowest possible temperature everywhere. It is important to focus on the critical parts of the machine. So it doesn't mean always it maintains less temperature, but it will protect the machine from the temperature rise. And coming to the testing, what are the different testings should be done for motor? Static, dynamic, and type test. The static winding resistance, winding inductance, and insulation resistance. And AC hypot and DC hypot polarization. This hypot measures the dielectric strength between insulation and ground, and how best it can withstand the over voltages. The over voltage is above the rated voltage, about 1.414 times of rated voltage under test. And the dynamic test, no load test, lock rotor test, cogging torque test, heat run test, continuous load test, and peak load test. The measurements are power, torque, efficiency, voltage, and torque. Whereas type test, cold test, dry heat test, temperature cycling. So cold test means you have to test your vehicle, especially for cold countries, sometimes less than 0 or very low, a bit less than 10 degrees centigrade. Dry heat test places like us, the temperature is always around. Sometimes in summer, our temperature is also reaching 50 degrees centigrade. So therefore, we have to carry out dry heat test and electromagnetic interference and electromagnetic conduction test. So therefore, it should not interfere its auxiliary or controller parts. So therefore, we have to conduct EMI and EMC tests. And IP tests, these are very much important, which are specifically called ingress protection tests. So that means there are some standards for IP tests, some IP 65, 67, 68, 69. Now the industry is always asking more than IP 67, 68. That is ingress protection means it is the machine are tested under dust environment and uh, water environment. So this vehicle is tested under completely dust environment because we don't know the vehicle movements and where it is going and how it is going and what kind of environment it is going to be faced. So therefore, it has to face the highly dusty environment as well as sometimes water dipping also. So therefore, these type of tests comes under ingress protection test and vibration tests and shock tests. It's known. And this is test setup for EV motor testing. In vehicle test, performance testing of the vehicle, powertrain and transmission, vehicle certification. Out of vehicle test, performance testing of powertrain, motor controller, transmission not included, electrical powertrain. So there is a chiller and there is a supply from battery. There are so see all these sensors measures data acquisition system. It measures sensors measures data and sends data to the data acquisition system. So traction inverter, traction motor, and this is load dynamometer, the load on the motor. And everywhere there is a variations in the its parameters plus or minus 5%, 0.5%, 2%, and 10%, 10%. So it depends. And all these measurements goes to the uh, CAN, as I told you, control area network, which controls and makes uh, appropriate decisions. Okay, and these are the standards for electric vehicles. Some standards for different parameters. So this is all about the motors. All about motors. Now coming to the EV controllers. So here the EV controllers plays an important role to control the inverter in order to supply the motor to improve the efficiency of the motor, in order to give more mileage, especially more mileage and long life. So the interdisciplinary nature of power electronics. So here we should not simply consider it is a power electronics. Again, it needs the knowledge and expertise about the other streams of engineering disciplines. So circuit theory, systems and control theory, signal processing, electronics, electromagnetics, power systems, sometimes magnetic, electric machines, simulation and computing, solid state physics. Okay. Apart from that, mechanical, packaging, prototyping, design for manufacturability, thermal analysis, suitable cooling system design. Success of any power electronic system is good electronic, mechanical, thermal design. So therefore, the success of PE system is good. It depends on good electrical, electronic, mechanical, and thermal design. So now the design approaches. So how to design a good controller. So therefore here there are three approaches. The one is customer approach. The customer comes to you and he will tell you his requirements. That is voltage range, frequency, and continuous current and peak current range. So they based on that you have to design a controller. Whereas in benchmarking, so there is some benchmarking is there. So one has to study and develop a controller from existing available controllers in market and functional testing of the controller. So after designing and developing, you have to test the controllers. Whereas the generic controllers, the generic specifications and ranges, that is of standardization, are with some standards. Based on the applications or type of electric vehicle, you have to design the controller. So it is a bottom approach. It is top level approach. And development process for controller available inverter stacks. So therefore here there are two uh, uh, ways to design controller for inverter. One is we will design a controller from the existing inverter stacks or available inverter stacks. So by taking available inverter stack, either Semicron or Infineon, Toshiba or Mitsubishi, you have to design a controller and testing and packaging and design prototype inverter ready. So how to develop our controller software or testing package. So here develop source code from MATLAB or Vsim, or generate C code using MATLAB or Vsim, PSM or embedded code generation tool. Then embed code in is ready. Otherwise, you have good controller EV mode. Development start controller. So hardware, software, mechanical design, thermal design, verification and validation, and testing. And these are hardware components: the power boards, MOSFETs, IGBTs, bus bars, separator boards, power connection terminals, and DC bus capacitors. Coming to the driver board, this is powertrain, driver train, MOSFET driver ICs, isolation ICs, DC bus voltage sensing, isolation power supply for driver ICs, interface connector for control board. And this is control board, the microcontrollers, clock, reset and communication interface circuits, power supply, outputs, driving circuits, interface connectors for power boards, input signal conditioning circuits, absolute and incremental encoders, to especially this incremental and absolute encoders to identify the location of the rotor of the BLDC motor or reluctance motor. Analog inputs, digital inputs, and any special inputs. Sensor board, the sensor circuit, so which has to measure speed, voltage, current, temperature continuously. And interface connectors for the control board. So you have to interface these parameters to the control circuit and connections to the power section. So this is the motor controllers for xEV. So this is a battery management system with the traction battery, motor controller, auxiliary battery. And these are the requirements. So handle peak power requirement, handle transient load and different driving behavior, handle acceleration and deceleration at full range of speed, isolated CAN bus for communication, reverse polarity protection, that is battery reverse polarity protection, short circuit protection, housing and connectors should meet required IP rating, that is ingress protection rating, and EMC and safety compliances, electromagnetic conduction and safety compliances. For hardware specifications, nominal battery voltage, maximum battery voltage, and peak current capability with time, continuous current capability. So this is the system configuration. This is the battery pack, and this is the inverter, this is the motor, okay, and this is the MCU control board. So for this, the inputs are electric brake input and battery voltage, battery pack, power supply, the program. This is the display to show the status, and here see Hall sensor, which gives Hall effect sensor, gives the position of the rotor of the electric motor, okay, and different the phase currents and pedal input. And this is the block diagram of the controller, the battery and auxiliary battery. So auxiliary modules. So here this is auxiliary battery is a DC to DC converter, which converts the voltage from battery rated voltage to the auxiliary levels, because here there are a lot of sensors. Suppose Hall effect sensor need around 5 volts, uh, 5 volts, and other sensors may need 3.2 volts. So therefore, the auxiliary power supply is a DC-DC converter which converts voltages to the control board voltage levels. And this is MOSFET IGBT driver, and this is the inverter. The battery supply goes to the inverter, and the auxiliary supply, from the auxiliary supply go to the gate driver circuit of this inverter, protection and isolation. So, and coming to the sensors, so here current, voltage, temperature detection, speed and brake signal, speed detection, and protection circuit. So all this go to the control board. Based on this, the control board takes actions and it generates the gate signal, which sends the gate signals to the inverter. So therefore, inverter uh, gives appropriate voltage to run the electric motor. And here there is a DC link capacitor. So this DC link capacitor is used to maintain the constant voltage, especially at the time of starting, which draws a large amount of current. And hardware, power board, inverter and control. So the power board needs the MOSFETs and IGBTs, bus bars, separator boards, power connection terminals, and DC bus capacitor. For an EV vehicle driver train, the main inverter is crucial component. This is similar to the engine management system for an ICE vehicle. So it's like a inverter is like a engine. So irrespective of the type of the motor, that is synchronous, asynchronous, or brushless DC, the inverter power board will be the same. Still, the control functions will be controlled by the control board and respective algorithms. The function of the inverter is to drive the electric motors as well as integrate the energy release during the regenerative braking and charging of the battery. The main inverter efficiency is directly related to the range of the vehicle. And these are the different softwares for design the controller. Here it is from 2016. Even in 2016 also we can do the same. And these are all the other softwares. This SIM, high-tech C compiler, and pads, simulation and design layout. Pads are widely used, Arcade, PSpice, and PSIM. And software, board support package, deterministic control algorithm, microcontroller side, calibration and data acquisition and diagnostics, PC side, calibration, data acquisition and diagnostics, and communication protocols. Coming to the mechanical design, component layout, any constraints, example, electromagnetic interference and electromagnetic conduction, minimizing the lead inductances, etc. So different topologies, packages, finalizing dimensions of the control board. I told you in the beginning of the motor, there are some softwares and FE tools to sizing in the designing of the motor. So like that here also. For thermal design, the natural cooling, forced cooling, water cooling, or any special cooling, heat sink design and water cooling channels, equivalent mode and analysis. For verification and validation, test plan and methods, software in loop testing, hardware in loop testing, testing on test bed, testing on actual applications. So test rigs, custom test rig for hardware in loop testing and evaluation boards. So galvanic isolation is one of the important isolation in the controller. Because what is galvanic isolation? What is isolation? So means to isolate two parts of the electric system. So here there are two parts of electrical system of different voltages. So no current flow between two parts or no direct conduction path. Exchange of information and energy is still possible. So what are those two? Why it is required? The power devices. So here two electric circuits, power circuits and control circuit. The power devices operates at 250 amperes current level, but control circuit operates at 1 to 10 milliampere level. So earlier I told you the auxiliary power supply or auxiliary battery. Auxiliary battery is nothing but DC to DC converter, which converts the voltages, high voltages to the low voltages to feed control circuit. So therefore, the control circuit operates at 1 to 10 milliamps, whereas power circuit operates at 250 amperes. So to prevent group loop current, ground loop current, and noise injection. Protection of digital controllers and communication systems from any failure in power circuits. Safety, isolating high voltage circuits from human interface. So example, 12 volts, 24 volts LV bus is completely isolated from main DC bus of 48 to 650 volts. So this is the main bus, 48 to 650 volts to drive the inverter, and this 12 volts, 24 volts, the LV bus, which drives the control system of the controller, or different sensors and memory and other auxiliary equipment. So type of isolation, there are three types of isolation: the optical isolation and magnetic isolation and capacitive based isolation. It is the self-explanatory. So here it transfers of electrical signal using light, here using transformer, here using capacitor. And power devices and controllers. So while designing the power devices, so there are, what are the different power devices and what are the parameters to be considered while selecting them? So major parameters are voltage rating, on-state continuous current, switching time, on-state resistance, and operating temperature. Coming to technology, so these are the devices: MOSFETs, IGBTs, okay, silicon carbide, and gallium arsenide nitride, and power modules. So this is simple switch. Basics of power devices. So these are four. MOSFET. So it has high switching speed, 10 to 500 kilohertz, low voltage, high current, and very low on-state resistance. So therefore low power losses, but lower short circuit withstand capability, typically 500 nanoseconds to 1 microsecond. Whereas IGBTs is it high voltage, high current, but low switching speed, 10 to 100 kilohertz. Whereas improved protection techniques, IPM and modules, and higher short circuit withstand capability, typically 3 to 4 microseconds. Whereas the silicon carbide transistor, high voltage capability compared to MOSFET, and higher operating temperature than MOSFET. So it's like MOSFET, lower on-state resistance and higher thermal conductivity. Whereas gallium arsenide nitride transistor, low on-state resistance compared to MOSFET. So still compared to MOSFET, here low on-state resistance. So therefore still the losses are very low, and small size for same voltage rating, lower gate threshold on voltage, and switching speed up to 500 megahertz. So without DC link capacitor, as I told you, the DC link capacitor, which is used to maintain the voltage, constant voltage at the time of especially starting its high current. So without DC capacitor, so it gives rise to 200 volt spike at the node. Whereas if you have DC capacitor, there is only 10 volt spike. Even in the variation of the current, it's a smooth variation in the current with DC link capacitor. So this is the DC link capacitor. So why DC link capacitor? Parallel to battery to provide stable voltage to inverter, protect inverter from voltage spikes from switching, protect battery, inverter draws smooth average current as it shown you, reduce the overall system electromagnetic noise. It also acts as a filter. And key selection parameters: permissible maximum DC bus ripple, maximum RMS ripple current through capacitor. RMS ripple current affects thermal performance, and the capacitor types are aluminum electrolyte or film capacitors. And the gate driver circuit. So here gate driver circuit used to turn on, turn off the switches like MOSFETs and IGBTs. So provide high pulsating di by dt current to MOSFET capacitors. Gate source voltage should not exceed safe operating area. Turn on MOSFET with 200 nanocoulombs in 200 nanoseconds require average 1 amp current during turn on. It's less. And this figure shows the turn on and turn off waveforms of gate drive circuit. And what are the auxiliary power supply design considerations? So isolation requirement, input voltage variation and output voltage variation, maximum output load, maximum transient and protection requirement, and EMC consideration. At the same time, cost should be considered while considering all these things. So sensor requirements for fault protection and control loop, current sensor, isolated current sensors, Hall effect based, current transformers, non-isolated current sensing, shunt based. Examples are LEM current sensors. Whereas voltage sensors, Hall effect based, isolated voltage sensors, which senses the voltage of the battery as well as the inverter as well as the controller. The temperature sensing, the thermocouples with negative temperature coefficient and positive temperature coefficient. That is the resistance decreases as temperature increases, whereas resistance also increases as temperature increases. Means positive coefficient, positive temperature coefficient, and negative temperature coefficient. Power losses, especially switching losses. The conduction losses when continuous current flows, and switching losses obviously. Switching loss, we have to reduce the switching losses. This figure represents the switching losses. So suppose here during turn on and turn off process. So DC link capacitors and gate drive losses. So wherever these switches are there, there is always switching losses. We have to consider them to minimize. Coming to the last part of the controller design, PCB design. The schematic, a symbolic representation of circuit components and netlisting, textual description of the connection between different components, bill of materials, that is list of the components with their part number and manufacturer details, footprint represents the exact physical dimension of a component, layout, physical interconnection of different components in the PCB design, and Gerber data, a format of PCB design data which is used to fabricate the PCB. So these are the steps involved in the PCB design: circuit design and component selection, schematic design, net listing, okay, and bill of material generation, footprint assignment, layout planning and footprint placement, PCB routing, and Gerber generation. I will show the. So here it is a 4-layer PCB, and PCB substrate, copper layer, solder mask, and silk screen. Where silk screen is a graphical layer used to component site to identify them and any other information. Whereas solder mask, thin polymer insulation layer applied on the copper track to prevent oxidation and solder bit. This copper layer, the connection between the components and carried out by this layer. Whereas copper track, connection between components in copper layer. Copper pore or fill. Copper is filled in a certain shape to connect high current components. So these are the 4 layers. I'll show these 4 layers are filled like this: 1, 2, 3, 4 layers. I'll show you. So this is prototype development of a controller. So this is EDA tools or software tools, and the circuit creation and simulation. So in a circuit, first you have to create the circuit simulation. After getting simulation results, depending upon the results, you have to finalize the different structures of the controller: design, layout, schematic entry, net listing, and error checking. So after this, the bill of material comes into picture. That is the number of capacitors, number of the diodes or number of switches, number of the ICs and their make and ratings all comes into picture. Based on that, here footprint creation comes into picture. That is where to place IC, where to place transistor, where to place capacitor, like that. So after that, routing of the layer. So the PCB will be routing and disconnected the shape of the PCB like this and sent to the jet spraying machine. Jet spraying. So it will this jet spraying machine deposits the soldering paste onto the PCB parts. Then it sends to the PCB machine, assembly machine. So here it picks and places the components. Different all the components are already placed in this machine. So this picks and places these components onto the PCB. Then it go to soldering. So there are two types of soldering machines are there, and then this is the machine soldering machine, which is used to place uh, the capacitors or not capacitors or the elements inside the board, whereas mounted elements are to be placed by this soldering machine. And these are the different ratings of the PCB machine, speed, acceleration, and all. These are the steps involved in the PCB machine. So this is a starting and this is ending. At the ending of the PCB will be ready, which is called populated PCB. Motor control overview. So these are all different motors. That is brushed motor, stepper motor, AC motor, brushless DC motor, and reluctance motor. Okay. So here the this represents the control complexity. So as you coming from top to bottom, the control complexity increases. Okay. So each machine has its own merits and demerits. Okay. However, BLDC motors and permanent magnet synchronous motors are highly used in electric vehicles because of its more advanced to other machines. And this is the control of synchronous motor. You know, vector control. You know how it is simple operation. How the synchronous motor operate. How induction motor operates. Okay, as the rotating magnetic field and induction magnetic field, when interaction between rotating magnetic field and induction magnetic field, it will produce the torque and control. So here here major thing is the rotor position is never known. We don't want the rotor position of the induction motor to control the induction motor. Whereas in BLDC motor or permanent magnet synchronous motor, there is a rotor. Okay, so here we have to the rotor position can be measured or estimated. We have to measure or estimate the rotor position in order to start the motor. So for that, here we have to place one Hall effect sensor which measures the position of the rotor, so that the rotor position is measured and control the permanent magnet synchronous motor. And these are the how to control the synchronous motor and BLDC motor. And the major here it is brushless DC motor and the permanent magnet synchronous motor. Both are back EMFs of BLDC motor as well as permanent magnet synchronous motor. Here, because of sinusoidal back EMFs, no torque ripple at commutation, whereas here torque ripple at commutations. Because of that, it will produce some noisy and not as efficient at low torques, and it is of low cost and it is of high cost. So as I told you here, controlling of BLDC motor with the trapezoidal back EMFs, it will produce the torque ripple at commutations. So first sample the system, position of the rotor first you need to identify, then three-phase voltages, calculate speed, frequency of the positions, then estimation without sensors, then regulate the loop and simulate the system. Similarly, this is V/F control of AC induction motor or permanent magnet synchronous motor. Okay, with multiple operating points, and it is equivalent circuit. Here, this RS, the setter resistance, it should not be neglected as Vm is less than V. And this is the final setup of motor between motor and controller. Okay, this is a motor and this is a controller, and this pipes represents the cooling system. Okay, here somewhere the water liquid enters into the controller and liquid comes out from the other uh, channel so that it gets cooled. And these are the equipments used in test rig. Okay, the resistance measurement and power analyzer and inline torque measurement, and these are the outputs. And this is the test bench, and this is the uh, uh, display, and it is the chiller, and it is the inverter, and it is the controller, it is the local desk, and it is the motor to be tested. Okay, and this is the load on the motor. This is the industrial test bench, integrated testing, motor controller, battery simulator. And this is one test result of one motor as well as controller. And here motor is tested for continuous power and continuous torque and peak power and peak torque. So at the time of starting, it has to generate the peak power and peak torque. Once the motor gets the synchronous speed, so it has to come to continuous power and continuous torque region. Continuous torque region. So this is tested for continuous torque. So once it matches your required data, then your motor design is absolute. Otherwise, you have to go to retest or redesign your motor whenever the continuous power and continuous torque is not matching with your required uh, uh, continuous torque and continuous power. This is all. This is the same peak represented again to understand better. Continuous torque and continuous power, peak torque and peak power. The peak torque and peak power, especially when your vehicle is moving on gradients, especially hilly areas. When you are climbing the hill, you need to spend more power to have more torque. Once the on straight road or motor gets synchronous speed, you have to your torque becomes low during high speeds. So I think these are some pics. These are the two vehicles which we developed, and these are the testings, and these are my team who are working in Bombay. That's all. Thank you. Any questions from me?
Okay,
Hello.
participants, if you have any discussions to discuss with the speaker, please ask them. Thank you very much, sir, for your valuable session on behalf of Department of Vvit and Vvit.
Okay, ma. Thank you. Thank you so much. I once again thank the convener of the program, head of the department EEE VVIT, and also the principal management of VVIT for giving me this opportunity to share my knowledge and views on this emerging area of electric vehicles in this 1 week workshop. Thank you all. Thank you for thank you all the participants for your patient listening. Thank you all. John,
Thank you, sir, very much.
am I leave?
Yes, sir.
Okay, thank you.
Participants, the next session will be start at 1:30 p.m. Thank you. Let us end the session.